This is a very quickly put together video just to try and help you with this week's physics work. Okay, I'm going to put a story to this graph because that's what distance time graphs are. They're stories about emotion. So in my story I've added a character. I have got a cute Westie dog, yes. So this is a very well trained Westie dog, okay. It starts next to me and I throw a ball. I'm really good at throwing, so 10 metres away this ball goes. And off the dog chases after the ball. But I said my dog was very well trained, so he sits and he waits for the instruction to return. So there's my ball with dog, 10 metres away from me, sat nicely. And I call the dog, so it runs back to me. A very obedient dog, so next to me this dog has come back, it's sat, and I throw the ball again, but a bit of a rubbish throw this time. Dog's waiting, I say, yeah, go on then, get your ball. And off the dog runs. Just 5 metres away this time, it was a bit of a rubbish throw. And the dog's a bit lacklustre about this. It's like, didn't really try very hard, did you? Off he runs though, and then just like before, sits and waits for me to call him back. That's the end of our story. That's the picture that our graph has built for me. Okay? So I've added some questions you can see here to try and break down the stages of the graph. And we're going to do them just as speed is distance divided by time equation questions first. Speed is distance divided by time. So a dog is travelling 10 metres away from me in 5 seconds. What is the average speed of the dog? Well, the distance is 10, the time is 5, 10 divided by 5 is 2, and the unit for speed is metres per second. So 10 divided by 5 is 2 metres per second. The dog is 10 metres away for 5 seconds. What is the average speed now? He's 10 metres away and he's staying there for 5 seconds. He's not moving, he's stationary. There is no change of distance in time. The dog comes back towards me, taking only 3 seconds now to return that 10 metres that it travelled. So now the speed is 10 divided by 3. 10 divided by 3 is 3.3, isn't it? I might be looking silly now. 3.3 metres per second. The dog stays next to me for 3 seconds. Describe the motion. Stationary. There is no motion. They're moving, not moving. Stationary, 0 metres per second here. Another word we use for that sometimes is at rest. That's a good motion term to sneak into the video. The dog runs away again. So if the dog's running away, this time it's only travelling 5 metres in 5 seconds. So we've got distance divided by time as only 1 metre per second. If the dog stays 5 metres away from me over 4 seconds, then for 4 seconds the dog is stationary again. 0 metres per second, or at rest. Okay. So we've used those questions to think about the motion of the dog instead of using the graph. But we're trying to learn about our distance time graphs, so let's link the questions. So this first question is the graph O to A, the second question A to B, the third question B to C, the next question is C to D, and then the next question is D to E, and the last question is E to F. I'm going to do all the stationary bits in one go first. So A to B, C to D, and E to F are all the same answer. What you may notice is on the graph, these are our horizontal straight lines. This means there is no change of distance while time is moving on. The distance isn't changing. So from A to B, the dog was 10 metres away from me and it stayed there. in this case for 5 seconds. Between C and D, the dog was next to me, stationary, for 3 seconds. And E and F, just 5 metres away from me, staying there for the 4 seconds we're shown on the graph. So in these motions, where you have this horizontal straight line and distance isn't changing with time, you're not moving. It's 0 metres per second because you're stationary or at rest. If we look at O to A next, right at the start of the graph, here distance is changing with time. And we can work out the speed from a distance time graph by using the gradient of that line. So here, the y value is gradient. It's always the y divided by the x. The y value here is worth 10 metres. The x value here is worth 5. So 2, 4, there's my 5 seconds, which is how I end up with 10 divided by 5 is 2 metres per second. If we look at D to E, in D to E, we can take the gradient again. Excuse my very poor drawing on the screen here. But we have got on the y-axis 1, 2, 3, 4, 5 metres divided by the x-axis, where we've got 1, 2, 4, 5 again, haven't we? Sorry, it's 5 seconds. 5 divided by 5 gives us 1 metre per second, which was the same answer we got up here. So B to C, now we can still use the gradient here. We can still do our y value divided by our x value to work out the speed. The difference is the angle of the slope, because the dog was moving away from us here and then he's coming back to us here. Is the direction that the dog is moving in, whether they're getting further and further and further away from us or getting closer and closer and closer to us. So this final bit on the screen right now will be B to C, and we have got our y value is worth 10 metres, our x value is worth 3, which is why we end up with 3.3 metres per second for that value. This graph here is, I've decided, all about a cyclist travelling along a road. Now you can see from this graph straight away that everything has a positive gradient, and that means this cyclist is just starting next to me, as it were, and travelling away from me through the graph. They never come back to me like the dog did earlier. So in this distance time graph there are 4 clear areas that we're focusing on. We've got A, B, oh, that was rubbish, wasn't it? B, C and D. Okay, so I'm going to focus on each of these sections, try and help you see how I can talk about the motion that I'm told, the journey that I'm told about from this now imaginary cyclist. So in A, the first thing I notice in A is that I have got a straight line. So that straight line, constant gradient, means that I have got a constant speed here. So that's the first thing I'd be saying about A. Okay, the graph isn't particularly steep. I can work out the speed by using the gradient. In this case, the y value is 200 metres. The x value is 50 seconds. So that would be 4 metres per second, wouldn't it? So I can say there is a constant speed of 4 metres per second in section A of the graph. If we move to section B, now section B is steeper. Okay, this gradient is steeper than A. So this is a faster constant speed. And again, I can use the gradient to work out exactly how fast that is. So this y value is worth 1, 2, 3 big squares. So that's worth 150 metres divided by the time, which is 10, 20, 30 seconds that I've counted along there. So that would be 5 metres per second, which is faster than 4 metres per second, as I predicted from the steepness of the gradient. Now in C, we've got one of those horizontal straight lines, and therefore we know immediately that nothing is moving. We're in a stationary 0 metres per second, no change in distance with the 10 seconds of time that we've got here. So the cyclist is at rest. Okay, so they were moving along, they started moving on a little bit quicker, and then they just stopped. So it's not a very realistic graph of what would happen in real life. It's a simplified version for practicing distance time graphs, but you could imagine they've had to pull up sharp because a red light, for example, that they've had to stop at. And then off they go again. So in section D of their journey, we can see that their speed, they've got a constant speed, because we've got a straight line again in section D. It's a constant speed again. But this gradient is really quite shallow. So this shallow gradient here, much shallower than A or B, means that that constant speed is a slower constant speed than it has been before. I'm expecting something less than the 4 metres per second. So if we have a look, we've got 1, 2, 3, 4. We've got 40 seconds of time. Sorry, I've done that backwards, haven't I? And we've got 50, 60, 70, 80 metres. I make that, I think, which would give us 2 metres per second, which is indeed slower than the 4 or the 5 was earlier. So, distance time graphs. This may look a bit confusing at first, but I'm going to use the colours to help me draw around it and try and give you a sort of summary of distance time graphs. So I'm starting with a line that we haven't seen a lot in this lesson, because it's a curved line. So this blue curved line is what I'm talking about at the moment. I've called it number 1. This is a changing gradient. So the gradient is getting steeper and steeper and steeper. Okay, that tells me that this isn't a constant speed. The gradient getting steeper tells me that the speed is increasing. It's accelerating. This is an acceleration. The speed is increasing over time. If we change that to think about the number 2, here we've got a decreasing gradient, really steep at the start, getting shallower and shallower and shallower and shallower and shallower and shallower till it is almost horizontal here. So, steep gradient at the start here, much shallower to a point at which the distance is not changing in time. This was going fast, getting slower and slower and slower. This is the speed decreasing, what we call a deceleration. Excuse my scribble on the screen. Right, number 3, and we're going green for this one, aren't we? Here we go. So number 3, we've got a straight line, okay, a constant gradient. So we know that is a constant speed now. And if we had values on this graph, we could work out that speed by doing y divided by x, work out the gradient, and we'll work out the speed in metres per second. So in 3, let's change the colour. There we go. In 3 here, we've also got a constant speed, but the gradient now is more shallow, less steep than it was in our green number 3. So we've got a constant speed, but it's a slower constant speed, because if we did our y divided by x value, we'd get less metres changing in every second. And then finally for number 4, we've got that horizontal straight line. No change in speed, no meters per second, stationary or at rest. I hope that brings those ideas together to make you feel a bit more confident this week. By trying the textbook questions this week, you might find that builds your confidence. So what I've done here is I've just shown you some worked examples from those textbook questions on our distance time graphs, so that you've got the option to take a screenshot and check your answers against them when you've tried them. I hope you found the video useful in supporting you, particularly with tasks 2 and 3. If you need another one for other parts of the lesson, you know how to get in touch and let me know.